All right. Excellent. Thanks, everyone, and welcome to this session. Uh, yeah, as G mentioned, this is our first talk in a special series on physics-informed AI that we're hosting through the Research Connection series. In this special series, we really aim to provide a survey of literature on this growing field of physics-informed AI by inviting external speakers like Dr. Youngsoo Choi, to provide their to give us a presentation on their influential research, which is really how this field is shaping, and forming as we speak. For today's presentation, it's my great pleasure to introduce Dr. Youngsoo Choi. Youngsoo is a computational math scientist at Lawrence Livermore National Lab. Before joining Lawrence Livermore, he was at Sandia National Lab and also at Stanford for postdoc periods. Youngsoo, for his research, he focuses on developing efficient reduced order models for various physical simulations that are required in multi-query problems like inverse problems in general, design optimization, and certain quantification. He's currently leading the data-driven surrogate modeling team at Lawrence Livermore, where he and his team are developing open source libraries such as LeapRon. All right, so without further ado, let me hand it over to Youngsoo, who will tell us more about his exciting work on latent space dynamic identification.
Awesome. Okay, let me try to share the screen. Thank you so much for the nice introduction, Hassan, and organizing this this speaker series. See you. All right. Let me see. Am I sharing the screen? Let me make it full screen. Do you see the full screen?
Yes, it's in presentation mode.
Awesome. All right. Well, wow. I just found out this is I'm the first speaker of this physics-informed, the data-driven, the ML AI, the speaker series. It's an honor. Wow, great. I mean, so yeah, as Hassan and you said, there are so many different exciting things going on under the realm of a physics-informed or physics-guided data-driven approach. Basically, they want to accelerate those simulations using the data and how you fuse those data with a knowing already known information such as the first principle. There are so many directions it has been already explored and more things to come. So there are many prestigious, like more famous speakers out there, but you chose me as a first speaker. That's a great honor. Let me start with that. All right. So today I'm going to talk about the framework, so-called the LaSDI, which stands for Latent Space Dynamics Identifications. And this work it's provide a nice framework so that within this framework you can tweak here and there and to generate a very diverse algorithmic the development. So I'm going to talk about that for sure. Okay, let me start with the motivations. So we always have to start with the physical simulations. Physical simulation, as you all know, has been one of the big things, like starting from the mid 20th centuries, thanks to the advance in the digital computer, right? Before we did all the scientific discovery and all those breakthroughs through some sort of, the famous mathematicians who work on the paper and the pencil and derive some mathematical stuff, and then, oh, this gotta be the governing equation. So this gotta be a, describing some, the fluid phenomenon or the electromagnetic phenomenon. And also the people and verify those equations by experiments, right? So that's how we did the scientific discovery, but thanks to the advance in computer and also the algorithmic developments, like such as functional analysis and finite element, finite difference, and finite volumes. These days, even more complex physical phenomena, it can be actually digitally realized through the physical simulation, right? You are looking at some of the examples here: powder bed fusion AEM procedure, pore collapse, 3D shape charge, electrostatic. All those things is wonderful and matches with the observed data or experimental data in very high precisions. And you can even extract the information which you couldn't extract easily through experiment, right? I mean, every single space-time corners, you can extract very detailed physical properties, right? The flow property or the energy property, momentum or entropy, whatever that, the quantity you're interested in. That's wonderful. However, the problem with that is as a human tries to seek more and more demands and more from these physical simulations, naturally the complexity of this physical simulation model becomes increase and increase. Because of that, this individual simulation, the computational cost increase and increase for even using the high performance computing, like very like a high rank in world classifications like the El Capitan, which is going to be available at Lawrence Livermore very soon. Even using those high performance computing, this individual simulation takes a week and hours. And I'm sure in your autoencoder, not Autodesk, you guys are dealing with such a physical simulations. So, but that's unfortunate because in order to, accomplish the scientific discovery, we need to accelerate them and explore the parameter space to conclude something, to solve the design optimization, so to solve the uncertainty quantification, right? So we definitely need to accelerate those physical simulations in order to speed up the scientific discovery. But thanks to the advance in AI and ML, like the data becomes another pillar we can take advantage of, and using those data now there are many the algorithms to accelerate these simulations. And as a one way, I would like to introduce a framework called the LaSDI, as I promised before, which stands for Latent Space Dynamics Identifications, and which starts with a data generation. So of course, I mean, we are going to use the data as a one important pillar. A lot of times we use the high fidelity simulation as a data generation tool because we are using that high fidelity simulation capability, the data size by nature is high dimensional. So it's hard to deal with those high dimensional data to fit those into some sort of model. So what we do is we compress that data into a reduced space. And once the data size is reduced, it's easy now for us to fit that into some sort of model. And in our group at Lawrence Livermore National Lab, we tend to model that reduced space, latent space dynamics using some sort of the differential equations. The reason we chose the differential equation is that it's much more interpretable than popularly used the black box neural network or some other statistical models, simply because we have been studying this differential equation since Isaac Newton era, right? Several centuries for several centuries, we've been studying these differential equations. We know there are robust, rigorous study, mathematical study on that. And so we know a lot more about the differential equations than neural network for now. So that's why we chose the differential equations and fit those data to identify these differential equations. In addition to that, what we do is we would like to make this model useful for the new prediction. I mean, of course, you are going to have data here and there in your parameter space, but if this model can only reproduce what you already have, that's not useful, right? So you would like to predict the new solutions using those existing data, and in order to do that, we parameterize this differential equation in the latent space. So what I mean by parameterization is if there is a parameter space you would like to explore, for the new points where you would like to come up with some solutions, you try to come up with a corresponding differential equation model in the latent space by relating those corresponding parameters into the differential equations, so that we do not have to, once this is built, we do not have to go back to the full space and deal with the high dimensional the space. We only need to solve these differential equations for the corresponding parameterized equations and get the solutions in the reduced space, which will be efficient and can be done very in an optimized way. So once that the solution of the differential equation is obtained, obviously what we do is we to project back to the full space and reconstruct the full data. And once the full data is given, you can post-process that data to come up with any interesting quantity of interest, any quantity of interest you would like to compute, like the lift-drag ratio on your wing, or it could be something else, right? So this is basically the framework of the LaSDI, and as I told you before, this framework gives you a rich the opportunity to come up with a new algorithm. So what do I mean by that? So let's look at the data generations. Just by looking at just one first step, just data generations, different types of the sampling in your parameter space is possible, like different strategy is possible. So for example, the a priori sampling, given the parameters in your parameter space, okay, I don't want to deal with how to choose those sampling points. Then you could use space filling kind of predetermined sampling approach, such as the uniform sampling or Latin hypercube sampling. It doesn't require any fancy the knowledge about the underlying problems you are dealing with. Easy to generate those point state, those sampling points, so very accessible. Anyone can use that. However, because we are dealing with the physical simulation tools to generate the data, a lot of times, as I said before, those simulation is very computationally expensive. So if you increase the number of parameter, the sampling points you have to generate, if that is increasing, the cost is increasing like exponentially. So ideally, you would like to reduce the number of the training data, if you can, because the generating those data is costly. So you could take the active learning or the greedy sampling procedure, where you have some sort of indicator to guide your sampling. So for example, the physics-based indicator, one I can give you is any data-driven approach is going to give you the approximate solution, right? And you can find out how good that approximate solutions is without actually computing the true solutions at that point. For example, by plugging those approximate solution into the residual computation of your full order model solver, that will give you the residual norm of that the approximate solutions, and take the norm of that. If that norm is high, then that automatically indicates that your solution, your approximation is not that good, right? Or if the norm of the residual is small, then that indicates that your solution is good enough. So those kind of physics-informed indicator can be used in the greedy algorithm. If it is high, then if some regions, if you see that if some region of the parameter space, if that is big, then you have to sample more there. And otherwise, you don't have to sample those areas, etc. You could also use the uncertainty informations. For example, Gaussian process kind of interpolation is used, then that also gives you uncertainty informations in your parameter space, and you can sample more where those uncertainty is high, and if the uncertainty is low, then you don't have to sample, etc., etc. So depending on what kind of sampling procedure you use, this LaSDI framework can be transformed into the different algorithm. Compressions, depending on the characteristics of the data you are dealing with, if it is, for example, like very diffusion oriented, then you could very efficiently compress those high dimensional data into reduced space with very compact representation. But if your solution is very advection dominated and so-called the Kolmogorov width decaying very slowly, or like if you do the SVD on the data and the singular value is decaying very slowly, then your linear compression technique wouldn't do a good job, because you have to increase the basis dimensions. And what's the point of increasing the basis dimensions if the basis is comparable to the full order models? The computational cost is not going to be reduced. In that case, nonlinear compression is going to be a way to go. So, for example, autoencoder is a very popular way of accomplishing those nonlinear compressions, and yeah, depending on your characteristics of the data problems, you could choose either linear compression or nonlinear compression. Identification, which I'm going to focus on in this talk, is another rate venue where you could branch out this LaSDI framework to more advanced data-driven algorithm. The first way of identifying your differential equation for the latent space is physics guided, like the projection-based reducer model. You probably some are familiar with. That's I'm going to introduce soon. And second way is the equation discovery algorithm. So we have the data in the latent space, right? And what we do is we provide some library of the form of the ordinary differential equations and feed those data into ordinary differential equation, and we identify the differential equation in that way. The third one is I'm going to introduce is the fixed form. So here, as your user, you decide what kind of differential equations you're going to use. It could be linear ODE, it could be quadratic ODE, it could be some sort of partial differential equation form, and we try to compress this high dimensional data so that reduced data it is generated by the compression will fit to that fixed form in natural way. So I'm going to talk about all that. And how about the parameterizations? There are different pretty much like unlimited number of options where you can parameterize this reduced space differential equation. You could use kriging algorithms, or you could use a hyper network, taking advantage of the expressibility of the neural network, etc., and etc. Anyway, I promised. I said I'm going to focus on those identification, 3 different identifications. So let's get into that. The first one I told you I'm going to go over the physics guided identification. All right, so the projection-based reduced order model is nicely fit into this LaSDI, the latent space dynamics identification framework. And it does give you a way of identifying those differential equations in the latent space in physics-guided way. So what I mean by that, okay, the compression in the latent space after the data is generated, the next step is compression. So here, same thing. You could use SVD, linear compression, or you could use autoencoder nonlinear compression. Get some reduced spaces. What I mean by the reduced spaces is that the reduced spaces that will compactly represent your solution space. So since once this reduced spaces is constructed, that will be your compact representation of your solution space. What you can do with that is you plug those representation back into the whatever the governing equations you are dealing with. If it is Navier-Stokes, yes, I mean you replace the state variable like the velocity, the energy density variables with these reduced spaces. If you're dealing with the structural analysis, elasticity, the problems, then displacement field, you replace this displacement field with reduced spaces and plug that in. And once you plug that in, the resultant, the equations, it becomes overdetermined system. Because since this representation is compact, the number of the unknowns now reduced from full order model size to the reduced order model size, where the full order model size could be million or billion degrees of freedom, or the reduced order model size, it could be 5 or 10 or very small. But you have still like billion or millions of equations, right? You just replace the state variable to be represented by this small number of coefficients, right? So in order to close the system, in order to solve that systems, you have to project the equation space, like the testing space in finite element functional analysis context. Once you do that, for example, Galerkin or Petrov-Galerkin projection can be possible. Once you do that, you end up with this familiar looking the differential equation, like as you can see, these ordinary differential equations. And by construction, you will see that we use the underlying, the governing equation, which describes the underlying physics, right? So this ordinary differential equation, which is reduced in dimension, is the physics-driven ordinary differential equation. So what do you do after you identify this differential equation? You solve in the reduced space for the new parameter and get the solutions and project back to the full space. Just as I described, how the LaSDI framework work, the projection-based reduced model exactly follows that framework. What is nice thing about this projection-based reduced model or physics-guided data-driven, this identification approach? Because we are not only using the data, because we are also using the physics, the governing equations, extrapolations and generalizability is awesome. So this the plots we have constructed the projection-based reduced model for the Lagrangian hydrodynamics problems, so-called the seed of blast, which I'm going to show you in next slide what that is. But there we parameterize the problem by changing the blast energy. So let's say we build a projection-based reduced model for the blast energy of 0.25 and just use 1 point and then build a projection-based reduced model. And then what we try to do is we try to predict the solutions for the other blast energy input parameter, which is obviously an extrapolation, right? But since we have used not only the data, but also the physics information, the governing equations to derive the differential equation in the latent space, the accuracy, the relative error does not increase, like the low fashions. Even though you go from here to very close to 0 or 0.5, which is like almost twice bigger than the original the blast energy, we still, for a lot of the position, velocity, and energy fields, still like close to 1%, or a lot of times you're less than relative error 1%. If you apply this extrapolation or generalizability for the black box approach, which does not incorporate the the physics, if you only use the data, then this kind of generalizability or extrapolation, you cannot hope to achieve that. It is only possible because the physics was incorporated in the problems. Very nice, right? I mean, the projection-based reduced model is very nice. A robust and great way of incorporating the physics into the data-driven approach. And because of that robustness, many variants of the projection-based reduced model has been developed. If I, just introduce some of the variants which we have developed at Lawrence Livermore National Lab, here is the first one, the space-time reduced pseudo model. Before, when I described the projection-based reduced model, I only have reduced the spatial degrees of freedom from million, billion to the 10 or 5, etc. Right? But if you're dealing with a time-dependent problem, you may have a very long time simulations. So number of time steps is like 1,000 or even like millions. So there is just the high dimensionality in time domain as well. And you don't only need to reduce the spatial degree. You could also introduce a temporal, the reduced basis in the time domain and reduce that the temporal degrees of freedom. That's exactly what we did for the space-time ROM, where we introduced both spatial and the temporal reduced basis and plug those space-time reduced basis representation back into the governing equations and derive the ordinary. If you do that, you will get algebraic equation, like the linear system of equation at the end, not the differential equations, because time domain has been reduced algebraically as well. So, but once you get that linear system of equations or nonlinear system of equations, which is time independent, once you solve that, it's going to give you like this whole space-time information everywhere in full space. So we have applied that to the transport particle equations, Boltzmann transport particle equations, which is notoriously known to be very high dimensional problems. And if I remember correctly, that time-dependent problem is the whole the degrees of freedom both in space-time was the 10 billion degrees of freedom, and using this space-time reduced model, we were able to reduce that to only 10 degrees of freedom, and meaning that you only need to solve the AX is going to be with a 10 by 10 the matrices, the block, the dense matrices. Once it is solved, we can reconstruct the whole space-time, the fields, and because of those rate reductions in degrees of freedom, we were able to obtain a speed of 2,700 and less than relative error, 1% relative error. Another variant of the ROM is this seed of blast, the problems I was referring to in previous slide, so-called the Lagrangian ROM, where you follow the model, not only the field is moving, but also the mesh is moving with the shock. In that framework, you not only need to generate the reduced spaces for the state fields, but also you have to follow where the mesh position is. So you build a reduced spaces for the mesh position as well, movement. And once you do that, it becomes the Lagrangian reduced model. And again, the great speed up and relative error was achieved. Okay, another variant, a lot of times the projection-based reduced model community, they use the linear compression, like the linear subspace social representation using the SVD. SVD is a very popular way of getting this linear subspace representation. But as I said before, if the problem is auto-vector dominated, then those linear subspace representation is not good. So in that case, the autoencoder type of nonlinear manifold solution representation would be beneficial, and we are the first group to come up with a the successful hyper-reduced nonlinear manifold reduced model. So I didn't go into detail what I mean by hyper-reduced, but if you're dealing with the nonlinear problems, and if you just simply introduce those solution compact representations and reduce the number of equations and number of unknowns, that's not enough to accomplish efficiency because there is a nonlinear complexity in the equations, and that scales with the full order model. If you don't do anything on that, then even though you reduce the number of unknowns and number of equations, overall the computational cost is going to be comparable to the full order model, or sometimes even slower than the full order model. So to reduce the complexity of the full order model and complexity of the nonlinear terms in the equations that scales with the full order model, you need to apply the hyperreductions, and we are the first group who came up with successfully the hyper-reduced version of the nonlinear Youngsoo model. By doing so, we were able to achieve a great speed up and the accuracy as well. All right, so okay, well, this is another hyper-reduction technique, so-called the SOPT, but I'm going to skip this slide. Just saying that we have improved the existing hyperreduction techniques by stabilizing some numerical behavior. Okay, so next let me move on to the very exciting topic. I'm personally very excited about this development, so-called the component reduced model, or I would like to describe this method as a data-driven finite element method. I'm sure many of you are already familiar with the finite element method, so let me start with that description. What do we do in usual finite element method? You first pick an element, right? It could be the tetrahedral element, or it could be some a triangular element or something else, right? I mean, but you pick an element, and then what do? You assign a polynomial basis usually, and you glue all those elements together to form some computational domain, right? It could be complex as it can be seen here, or it could be simple. But whatever the computational domain is, you form that by assembling this individual element together. And then what do? You solve the underlying partial differential equations, or whatever the governing equations you have to solve for given physics problem. Okay, so what is then the data-driven finite element method? Data-driven finite element methods simply replace those polynomial bases with data-driven bases. Why do we want to do that? It's because if you just use the traditional finite element methods and use the polynomial basis, if you think about it, those polynomial basis does not know anything about the underlying problem. Does polynomial basis know anything about the Navier-Stokes equations if you're solving Navier-Stokes equation? Does the polynomial basis knows about your elasticity problem? No, it doesn't know anything about it. So because it doesn't know anything about it, in order to increase the accuracy of your finite element method, what people normally do, you apply some refinement, right? H refinement or P refinement, increase the order of the polynomial, or increase the order of increase the number of elements, right? So that the responsibility of those individual polynomial bases is reduced. Like as you decrease the size of the element, the polynomial basis that has to represent the solutions becomes smaller and smaller and smaller, so that it doesn't know anything. It doesn't need to know anything about the physics problem, underlying physics. But if you replace the polynomial basis with the data-driven basis, which knows about your physical problems through the data, then we can improve the quality of the polynomial basis greatly. Then we can increase the size of the elements greatly, so that we can actually take the larger time steps. Like the numerical stability, it becomes improved, etc. and etc. So that's the whole idea of this data-driven finite element method. As I described before, you could take a linear subspace data-driven basis or the nonlinear manifold data-driven basis, but the key idea is when you construct the basis for the finite element method, it lets you use data, not only the just the statistically formed some prefixed form of the polynomial basis. A lot of benefits, as I said, you can take the a much larger scale problem than traditional FEM, because you can take a much larger size of the elements with these complex representations. And also you can enable arbitrary shape of elements. I'm going to show you what I mean by that by demonstrating this data-driven refinement method in next slide. And also, different types of the refinement is available. Instead of H refinement or P refinement, you could think of the D refinement, where you can increase the rank or the basis size of basis dimension of the data-driven the basis representations and increase the accuracy, even faster way of the convergence ratio. And also, as I mentioned briefly before, thanks to the hyperreduction techniques, we could apply this data-driven refinement method to the nonlinear problems with no issue. I mean, I already talked about this, and also I talked about this. Like you can take the larger time steps, so increase the numerical stability condition, etc., etc. Okay, so what if you think about it, what we really achieved using the data-driven finite element method is this phrase called the train small and model big. So what I mean by that, so first example, we have applied this data-driven approach is actually the design optimization problem. Let's say you would like to model some elasticity, the physics onto lattice structure, because the lattice structure is very, very complex in geometry. If you just use the traditional finite element method, a lot of degrees of freedom you have to introduce if you apply the H refinement or P refinement. Instead, if you come up with a element shape, which is, which can form this lattice structure, the underlying lattice structure in assembling way, like this cross shape or the strut shape, the straight strut shape, and or the circular, the joint shape. Once you build the reduced basis for each shape, as you can see, these are the arbitrary shape, right? Once you build the data-driven basis for each component, each element, what you can do is you can assemble those together to form some sort of the lattice structure here. And what we actually solved here, initially it was L bracket shape and filled with all the lattice structure everywhere here, and we actually solved the topology optimization, right? Asking those optimization to get rid of unnecessary the component, lattice component, and then also not breaking it under some boundary conditions and external force, and come up with the lightest structure. And this is the lattice structure it gave us. And since we use the data-driven finite element method, the individual, the elements, the number of degrees of freedom, the data-driven we need to cap was like only 6 or 8. And imagine that, in order to solve this L brackets using that data-driven finite element method, you only need to solve very small system of equations every time, and that was very great feature to actually solve the topology optimization, because you have to go through, iterations. Every iteration you have to solve different full order model problems. At the end of the day, we were able to achieve like great speed up and accuracy as reported here. And this was the linear problem. How about the nonlinear problem? Yes, as I said, thanks to the hyperreductions, we were able to extend that to the nonlinear problem. As a demonstration, we solved the porous media flow problems using the Navier-Stokes equations. And here, each element has a different types of shape: circular shape, triangular shape, and the star shape and the square shape. And once the data-driven basis is constructed in each element, what we do is we assemble them to tackle the much larger system of porous media domains, and basically doing following the data-driven finite element method, we were able to achieve like scale up of 256, because all the training only need to be done in the smaller scale, this element size, and actual solve we can enlarge, scale up the size greatly once the data-driven base is constructed. How about the time dependent, and how about the nonlinear manifold representations? We were also able to, use the autoencoder type of nonlinear representations and solve this time-dependent nonlinear 2D Burgers problems. The training was done in this 2x2, the very small scale, the size. And then once the data-driven, the nonlinear manifold autoencoder-based representation is constructed, just following the data-driven finite element method, the framework, you assemble them together and enable a much larger, the system. And yes, I mean, I think this data-driven finite element method approach is very promising, and I think that it's a great interest to you guys as well, the autoencoder. So I will be, very grateful if you further investigate this type of method and work together with us, and that'll be awesome. Great collaboration, right? All right, so right now looks like I have only 15 minutes left. Let's try to go into the next identification approach pretty fast. So I promised to introduce the 3 different identification approach. The first one is the physics-based one, which I'm just done with. The second one was the equation discovery-based identification. And many of you are probably familiar with the SIND, the sparse identification of the nonlinear dynamics problem, the algorithms which developed, popularized and developed by Brunton, Proctor, and Klutzin from the University of Washington. And what they do is, once you have the data in the reduced space, as a user, you can provide any types of nonlinear functions to form the initial the form of the ordinary differential equations, right? But once you provide those library, what you don't know is the coefficient in front of those nonlinear functions on the right hand side. So in order to find out the corresponding coefficients, the SIMD is solving the least squares, the regression, the problems by using this data and minimizing the difference between the derivative terms and those coefficient times the nonlinear function terms. And also they sparsify it so that to find out, in order to make many of these coefficients zero, so that unnecessary nonlinear functions on the right hand side is dropped out, and try to come up with a parsimonious, the ordinary differential equation form. So that's the basic idea, but it has a problem with it though. Since they are using the strong form, if the data is noisy, it's not robust at all. I mean, think about it. If the data is noisy, then the data in the reduced space is going to be noisy. And imagine taking the time derivative of that noise data. It's not going to give you any useful information. So as expected, we have tried to introduce the noise, like the Gaussian white noise, like 10% noise with respect to your field variable, and apply this LaSDI approach using this strong SIND form. And as expected, it doesn't perform well. The relative error is 40%, not good. But fortunately, there's several ways of fixing it. But one way we have adopted is using weak form. So how do you form a weak form? First, you introduce a test function, smooth test function, whose derivative you know everything about, because you have a choice to what kind of test function you're going to use. So introduce that, multiply both sides, the left and right hand side of the strong form, right? And then you take the integral, and when you do the integral, you do the integration by parts, so that this derivative on the data, noise data, is moved to the test function. So that now in this weak form, you don't have to take the derivative of the noise data. You just take the noise data and then multiply by the derivative of the test function, which you know everything about the derivative. So that's the great effect of this weak form. But another great effect of the weak form is, since this is integral, is play a role of the filtering. So the noise data, it becomes a smoothed out and handles much more robust questions. Okay, the same, the noise data, 10% noise data, where the strong form, the LaSDI was very struggling before. Now if you use the weak form, then great things happen, right? I mean, the 40% relative error reduced to the 5.6% relative error, and in eyeball known, it becomes very close now. Okay, let me skip this this application side. I mean, we have successfully applied to this equation discovery based the LaSDI framework to the pro-collapse simulations. Wonderful, with some tweak, wonderful. The results was obtained, and also we have successfully applied that LaSDI framework to the whole round problem, which is these days a big thing. Because recently, the Livermore mentioned that, like 2 years ago already. The time flies. 2 years ago, the first ignition, like the fusion ignition, they experimentally proved that that's possible, right? The amount of the input energy you put, and after the fusion, we were successfully output like larger the energy. So opening the door of like the new type of the energy and tons of money now is going to that inertial confinement fusion types of the problems. And core of that, the ICF, is this all round problem where you apply the radiation or the thermal source terms, and then that's going to hit the target, the capsule in the middle. It's going to show up right here. And then here, in order to make those fusion ignition possible, we need to make the thermal, the distribution of the capsules on the surface as uniform as possible. So we kind of have to solve some sort of optimal control or the optimization problem. And obviously, the whole run problem deals with the TRT problem, thermal radiative transport problem, which is known to be very high dimensional. So it's very computationally expensive. So we apply the LaSDI to accelerate them. And yes, we were able to successfully accelerate them using this LaSDI work. Okay, the last identification approach I would like to introduce is the fixed form identifications. Let me just briefly introduce the first form of the fixed form, which is well known to a lot of people, so-called the DMD, which stands for dynamic mode decompositions, and where it uses the linear compressions, and as a fixed form of the ODE in the latent space, they use the linear ordinary differential equations. Not exactly they are using this continuous form, but they rather use the discrete form in original DMD, but the idea is similar. And let me actually skip this DMD part because it's probably many of the people are already familiar with the DMD. So we have successfully applied that to the 3D printing, the problems, and also we were also extended that DMD to the on-the-fly the framework which I presented in the WCCM, the past WCCM, and since keep assuming that a lot of people are already familiar with the DMD, let me end my presentation by introducing this last topic, which is another exciting topic in my personal opinion, so-called the thermodynamics-based LaSDI. So this is also fixed form, using the fixed form of identifications. It used the autoencoder. You could use the SVD type of the compression. It doesn't matter. But in the latent space, we use specific partial differential equations, so-called the generic equations. Why did we use the generic equations? Because it has a weight property. So when you form these generic equations, there are 4 different operators: L, E, and M, and S. E is the energy, and S is the entropy, and L is the friction, the Poisson matrix, and M is the friction matrix. And if those operators satisfy these 4 properties, like the L being skew symmetric and M being the symmetry positive definite, and all 2 additional conditions, then whatever the solution you get from this generic formalisms, it's going to automatically satisfy the thermodynamics laws, like the first and second thermodynamics laws, conservation of energy, and then entropy always increase, etc., etc. Very nice. And by choosing this generic formalism as a latent space dynamics identification fixed form model, what we can do here is we can relate these thermodynamics in the latent space, like the energy and entropy, to the full space dynamics in actual problem. It doesn't matter your actual the governing equation, the full order model is thermodynamics related or not, but whatever things happening in the full space, we can relate that to the in the thermodynamics, the terminology. So I'm going to introduce what I mean by that. But before we do that, we have to do one more thing. One thing we have to accomplish. Right now, this generic formalism equation is not data driven. But now in the LaSDI framework, we do have a data in the latent space, which is the compressed data. So we have to somehow make this generic formalism data driven. So like learning individual operator using those data. Of course, we have done that. GFINS, is the data-driven version of the generic formalisms, and the individual operator is represented by the neural network SN and LNN. And then, of course, we put the constraints so that these four constraints are satisfied. And then it becomes the data-driven generic formalism algorithm, and we use that form in the latent space dynamics, the identification steps. Okay, let's apply that to the first, the simple example, 1D invised Burger's equations, and as you probably all know, like the 1D for the Burger's equations, we start with the Gaussian initial conditions, and as time progresses, the shock is formed at the end. And then we noticed what those energy and the entropy, the variable in the latent space does. Let's actually look at the entropy. Of course, it's going to increase because it satisfies the second law of the thermodynamics. But if you look at the rate of increase in the entropy, then it does pretty interesting things. In the beginning, the rate of increase is not that big, but later on it increases even further. And we observed that corresponds to the shock forming in the 1D invised Burger's equations. Initially, it was smooth initial conditions, so that corresponds to the slow rate of increase in the entropy. As the time passes by, the shock is formed, and that triggered in the latent space the entropy to increase much higher. How about the heat equation? It's kind of doing the opposite things, right? I mean, you start with the bump initial conditions, and after the diffusion, everything is smoothed out, and that was also captured by this entropy rate of increase. Initially, it was big, and then later on, it goes down as we expected from the diffusion process. Initially there was some bump, and then it all smoothed out. So why am I excited about this? It means you are effectively doing some change of coordinate. So let's say you have the high dimensional problems, right? And whatever that is, it has some characteristics within that high dimensional coordinates, right? And then we apply the autoencoder, and we ask the autoencoder to feed the data and compress the data so that it fits into this thermodynamics, the latent space, the models. And by doing that job to the autoencoder, what we are actually doing is change of coordinate, change of variable, so that whatever it's doing in the full space, we map that into the thermodynamics context. So that once this model is built, and just by looking at the characteristic of those energy and entropy thermodynamics quantity, we can deduce what's happening in the full space. We don't have to go back to the full space and analyze things. We can do, if you can even do the analysis in the reduced space, which will be very efficient and future will be very efficient, right? So that's why I'm pretty excited. And this thermodynamic is based, the LaSDI is just one example. You could come up with any different types of physics equations and introduced it as a latent space dynamics as some sort of the fixed form, and then relate that into the full space dynamics. Okay, with that, let me actually conclude the talk, but a lot of the things I have introduced is actually available as an open source. So it's called the Libram.net. It summarizes all the capability we can do with this open source code, and you're welcome to just go there and then grab it and take advantage of it. And if you want to know more details about this reduced flow model, you could go into the YouTube tutorial. And we also enable the cloud computing so that you don't have to compile things. Once you have access to the AWS, then you can just take advantage of already compiled the examples of the Libram, and you can just play with it. Okay, let me end my talk by recognizing awesome collaborators. Without these collaborators, I wouldn't have been present this exciting stuff. Okay,
All
well,
right.
that's it. I guess
Thank you so much. That was an impressive body of work. Thanks for this awesome presentation. So we can stay a bit over time if folks are interested, or if you're also available. But if you have questions, please turn on your camera and raise your hand and speak up, please. Meron?
Yes, thank you very much. Very interesting work. And yeah, and especially the component-based reduced order modeling that you mentioned. It's very closely to my fields of interest. And I have a few questions. Maybe it's just some sort of brainstorming, maybe. So my main question is, have you tried applying this concept to advection dominated problems? So that's one question. So maybe if you can answer that, and then I'll have a follow-up question.
Okay, well, this third one is obviously advection dominated. It's purely advection, right? As you can see. And in order to capture that, we intentionally use the nonlinear manifold solution representation, like the autoencoder type of neural net type of the solution representations. But let me leave this remark though. I don't think the nonlinear manifold solution representation is really desperately needed to capture these advection dominating problems. Polynomial basis, in the traditional finite method, if you look at the structure of the polynomial basis, there's no reason those polynomial bases should capture those advection dominated problems, but it does. Why? Because the only job that they need to capture the dynamics of the advection is very small element, right? So, so in that sense, I do believe that although we did use the nonlinear manifolds solution representation to capture these advection dominated problems, because we are the individual, the basis, the responsibility is just capturing the dynamics in the smaller scale. I do believe that if we have tried the linear subspace solution representations, it could well be the capturing those advection dominated problems. So that's another beauty of this data-driven sign out.
That's good to hear. So do you think this idea is applicable to turbulent flows as well?
I do think so. That's actually the pathway we are taking. Now we start with the linear problems and move to the nonlinear time independent problem, and we also move to the time dependent nonlinear problems, and we are working on the time dependent the Navier-Stokes equations right now. And after that, what's next? Turbulence, right?
Okay.
Obvious
Fantastic.
next step. Yeah.
And so I have one more question, because there's Jamie also has a question. If you go to the previous slide where you have a picture.
Oh,
Yes. in here. So if you were to do component use, like you want to apply component-based reduced order models to such a structure that you have in this picture, how would you solve this problem using component-based reduced order models? Because this specific structure is not sort of a component-based system. So how do you imagine such a technology would be applicable to this kind of geometries?
But do you agree that this domain can be assembled using this tetrahedral element?
Sure. Yes. Yes.
Sure. Okay, cool. And the traditional file element method, what does it do? It has a reference domain for this tetrahedral, and then map that element to individual computational corresponding domain by distorting these elements a little bit, right? So there's the map defined from reference domain to the computational domain. So we can do the same thing in the data-driven file element method. You build a basis on this reference domain, but parameterize so that the basis can handle those map between the reference domain to those distorted domain. And once that parameterization is done and that is incorporated in the generation of the data-driven basis, then you can freely distort those the element to form still using the tetrahedral, right? But distorted it so that you can complete the assembly of this complex.
Okay, so you want to find the basis for this tetrahedra that is more suitable to the actual physics that you're trying to solve. Okay.
Exactly. Yeah.
Okay.
Jenmi?
Hello, hi, Youngsoo. Thank you so much for the great talk. I feel like I'm gonna add all of this to my reading list, so definitely would be interested to learn more. So my questions are kind of high level. So the first one is actually related to the very last one. Is it
thermodynamics?
Yeah, that's right. I'm just kind of curious. It looks like you are able to quantify the uncertainty in the prediction. So I'm just kind of curious, where did that come from? Is that kind of inherent part of the equations, or is there some sort of probabilistic, kind of features added to the neural networks?
Right. So how did we do that? So I think we used the variational autoencoder or the neural network to also give us the standard deviations.
I see. Okay, great.
But I need to get back to you on that in order to answer that questions precisely, though, because I don't remember how we come up with these standard deviations, to be honest.
Okay, yeah, that would be great. Thank you. And then the other question is also on this work. I think you mentioned the ability to incorporate known physics. Could you elaborate on that? Or how is the known physics incorporated into the learning of these?
In this LaSDI framework?
In the GFIN, I think on the previous slide, probably, or here. Oh wait, hold on. No, maybe which slide is that? Sorry.
This one. I think in the beginning I talked about the physics guided identification using this.
I think it's the one with the generic formalism informed neural network. So it's I think so the three conditions. Yeah. Flexible and leveraging available physics. So I'm just kind of curious, how did you do that?
Well, I mean, what this bullet points was, if the full order model is the thermodynamics related, then what we are doing is we intentionally use the fixed form in the latent space as a thermodynamics. So there's a clear connections between them. But that's not what what I did not mean was to identify those the equations using those available physics. That's my first part of the identifications. First option of the identification I have introduced in the beginning of the presentation. Yeah, that's not what.
Oh, right. Okay, thank you. One more question.
Actually, can I also ask a question? I also have a question. Sorry, you had another one, Jenny?
I do, but you could go first. I can come back.
Thanks. So on this slide that you were discussing with Meron on the basis functions, and the one that we're showing the component based from.
Oh, component. Okay. Okay, let me go there. Where is it?
So
Yeah.
that got me thinking. So in the next one, essentially, which lead, yeah. So when you're building the training data set, you're essentially also you're assuming some basis functions. So to truly
Oh, yeah, basis function, you mean like the form of the basis, like
Yeah.
the either linear subspace or nonlinear manifold.
Yeah.
Yes.
So to truly make it you know, learnable, if the solver is differentiable, that you could make that basis function also something that could be trained. I'm wondering if you could also train it while you're, I mean, train those basis function even for those, you know, for those basic components, without even assuming, you know, that there is this
Any
conventional,
form?
yeah.
Well, okay, so that's, yeah. So, you know, I just, you know, as an option of generating those data-driven bases, I just introduced the linear subspace and nonlinear manifold representations. But you could think of applying the Cindy type of approach. Once you have the data, you can feed that into the Cindy, and you can come up with actually data-driven polynomial basis, right? You can think it that way. Or if you want to be really, really general enough, you want to be general enough, you don't need, what I mean by the general enough is that, as you just exactly said, like we don't want to assume any form of the basis. You just want let the data figure out what kind of form of the basis you want to use. If you want to do that, then you can apply, you know, what is it called? The symbolic regression type of approach, where their search space is it's not assuming any specific form. It assumes like, oh, use plus sign, minus sign, differential operator, use this variable, X variable, Y variable, Z variable, or this time variable, or this, yeah, and so on. You just provide those primitive components, and then using data, okay, come up with whatever the optimal form of the basis form. Please come up with it. So you can do that. You can also do that. But as you do that, as an experiencer of that symbolic regressions, you are actually, you know, increasing the parameter search space size, like pretty much unlimited, like very big. So because the search space is big now, it's hard to you know, get some fast convergence on any form. So I saw the drawback. Like, I mean, we tried to do that you know, in the past, but because the search space is so big, the convergence was very slow, and a lot of times it just you know, converges to the local minimum. It's not even close to the optimal form, and so it was not giving us a, you know, the practically efficient and robust the basis form. So that's why for the practical point of view, is providing some form of the basis would guide, you know, this algorithm to be efficient and practical.
Awesome. So maybe one last question from anyone. So I just want to give the.
Oh, well, Jamie had
Do you want to just ask your question? Yeah.
Sure. Yeah, so I guess it's a more of a high level, just a broad question. So it kind of like is there like a trade-off between kind of flexibility, like say, you know, if we're using kind of like an autoencoder, encoder decoder type like neural network to do you know, the compression instead of doing POD. That's more expressive, and I think it also has advantage in terms of being a nonlinear approximation. How is it trade-off with the amount of training data that's required? And I think that's kind of maybe connects back to the point of learning the element basis as well. Like, I think, you know, I think we can always make it more expressive, but that also means that maybe more data would be required. So do you have any sort of, from your experience, or any comment on that?
Yeah, well, my answer to that is you just already spelled out exactly that. Okay, so if you go from linear compression, nonlinear compression, obviously nonlinear compression has more expressibility, but the training that is a lot more expensive than linear compression. SPD, because of that, it can be easily applied to the very, very large scale problems. But imagine that training those nonlinear the autoencoder on very large scale problems, even using the high performance computing we have at the lab, it may well take whole machines for several days just to train that that autoencoder for the truly large scale data. So that there's a pro and cons, obviously. But if you just go into this data-driven finite element method context, because the training is intentionally done in the smaller scale, the size of the data is much smaller. All of a sudden, that neural network training becomes not a problem, because this accomplishes this model, like the train small and model big. Once the neural network is trained on the smaller scale, which can be done easily because the small data size is small, and you can take advantage of the expressibility and apply that to much larger scale problem by assembling them together. So yes, so this component one or data-driven finite method is opening the window of taking advantage of this neural net expressibility without penalizing those the disadvantage of the expensive training cost. So yes, I mean, wonderful points, Jamie. You just nailed it.
Oh, thank you. Thank you for your answer as well.
All right, so maybe we can end on that high note. So thank you so much, Youngsoo, for this wonderful presentation. It was really informative. I also appreciate your time. I'll be in touch once we have the recording. I'll share it with you. And thank you guys for joining this presentation. All right, have a
Thank you so
wonderful
much.
rest of your day.
Thank you.
Thank you.
Bye.